Okay, vectors.
Lovely.
Vectors, they're like pointy arrows and stuff. They can go in all kinds of dimensions. First, I would like to convince you that you already know a very great deal about vectors, like this. So, the real number line is a representation of all the real numbers, right? Which I'll put a few up here. And so the thing about vectors are a length and a magnitude or direction. So basically it's an arrow pointing somewhere that's going in such and such direction and it's so long. When we say the number 3, just seeing 3, this is magnitude. What's the difference between magnitude and the vector in some specific instances? 60 miles per hour is not a vector. It's a magnitude. It just tells you how big, or in this case, how fast. 60 miles an hour southeast is a vector, okay? And of course, for the length of the vector, you can decide, you could let it be the 60 miles per hour. I mean, vector length doesn't have to be length like we think of length. It's just arbitrarily what you're going to decide is defining. It's called a metric. It gets really cool stuff. But this is what I mean. You see the number 3, generally it's a magnitude. It's like I have $3 or something. There's really no direction. But the truth is 3 can be thought of as this vector right here. Oopsie, it's supposed to be straight. So 3 is going in the plus direction and it's 3 units long. Notice we can also, so 3 and minus 3, they're different. How are they different? Well, obviously, the real difference is that it's which way they're going. This is minus 3, right? When you do the absolute value of minus 3 is 3, really what they're doing is stripping off the direction in the minus direction. This is 1, 2, 3 away from 0. Just like the absolute value of 3 is 3, this is 1, 2, 3 away from 0. So you already know a lot about vectors, and quite frankly, I talked about it in some of the earlier lectures because the complex plane is a perfect place to start thinking about vectors. Today, we're going to stay in the real plane, and unfortunately, the book that we're using right now doesn't go into 3 dimensions. And when you get into physics, those of you who are going, general relativity will take place in 4 dimensions. You can have actually infinite dimensions, infinite number of dimensions, each with infinite number of vectors, and it becomes very, very neat. Okay, so here is our typical plane, and let's do 1, 2, 1, 2. I'm going to make this up because it will be easy to deal with. So here's the point 1, 1, here's the point 2, 2. I'm going to make a vector out of this line segment, and the line segment is here. This is called, well, I'll use different color for this. This is called the initial point. I-N-I-T-I-A-L. I was slipping there for a second. This is called the terminal point. And sometimes it's called the head. It seems reasonable, right? So this vector has a couple things. It has magnitude and direction. What's the magnitude? Well, the magnitude is simply going to be the length of the vector. And in the real plane, what is it going to be? It's going to be 2 minus 1 squared plus 2 minus 1 squared square root. This is the square root of 2, right? And we know what this is because look at the triangle we're making. Actually, let me get this out of the way. 1, 1. So if this is drawn a little better, here, the distance here is 1, the distance here is 1. Clearly, this is the square root of 2. And because, I mean, this cuts the y equals x axis right here, I made this at 45 degrees or pi over 4 degrees on purpose. So this vector right here has a direction and a length. And we can represent it in several ways. But one of the most convenient things about vectors is that any vector that has this length and this direction can be considered equivalent. So there's another vector equivalent to this starting at the origin, and it just makes it really easy to do computations. So here is this vector, right? And hopefully you can see this is from 0, 0 to 1, 1. These are the same, they're located in different directions. And basically what you're gonna wanna do is translate your vectors from the origin so you can start constructing things and dealing with them. Some notation. Okay, so incidentally, if you have a vector u, and we usually, in your books they'll put this in bold, and usually vectors are u and v and sometimes w. Because I can't write in bold with these, I use the little arrow top on it, and this is pretty typical in most classrooms. If you have a vector u and a vector v, and they both have the same magnitude and direction, they're considered equivalent. Okay, so they're considered equal, even though they may not be in the same place. Oh, another thing too about this. Usually when you do this with vectors, a lot of times this is a point, right? This is going to be the point P, this is the point Q. Oftentimes I use P and Q. This vector may be represented like this, from P to Q with an arrow over it, right? It's very standard notation. More notation that you need to know, and that is the norm of a vector. And I guess I'll bring back the t-shirt of semi-disgust and say hello, hello, and clean up the board a little bit. Okay, some more notation. In 2 dimensions, we're going to write our vector v like this. Typically, it can be like this, where these are the coordinates. So what I mean by this, we're going to shift everything to the origin. And if I say this vector v is, in this bracket notation, this is the vector AB, this would be like this. 1, 2, 3. I'll just call this A, and 1, 2, 3, 4. This is B. We'd go to this point. So here's, basically, this is like a point in regular coordinates. This would be right here. This would be the vector v with coordinates AB, right? The norm of the vector v is its magnitude. It's how long it is. And this is given by the old classical Pythagorean formula, a squared plus b squared. If we're in 3 dimensions, and I'll show you the case of 3, even though this book doesn't, hopefully the instructor who uses this will get a better book, a tougher book, a more interesting book, I mean. If this vector was this, A, B, C, in 3 dimensions, then the norm of this would be the square root of a squared plus b squared plus c squared. This particular book, we're not using this, okay? Vectors, oh, there's vectors and scalars. So what's the difference between this and this vector? We'll call it kv, which is k times ab. Well, scalars, and what I mean by this is a scalar. This is just a number. It has no direction. It's just telling you how big. This can go inside. This is the same as Ka, Kb. So what's going to happen, assuming that K is greater than 1 in this case, basically it's just going to stretch it out or shrink it. And I'm going to let K be out here. We'll let this be Kb, and this will be Ka, whatever K was. And what happened was is that this ended up stretching this. This would be Kb. And my producer has just told me I have to wrap up this particular segment. So look, stare, behold, and be wondered, the great world of vectors.